Have you ever thought about how a piece of mail actually reaches its destination? To get a letter exactly where it needs to go, the post office relies on four specific pieces of information: the state, the city, the street, and the exact house number. It turns out atoms use an almost identical filing system. Instead of sorting letters, an atom has to keep track of its electrons, sometimes dozens or even over 100 of them moving at once. It needs a reliable way to organize them all without losing track of a single one. Scientists use what they call quantum numbers as the scientific equivalent of this four-part address. It's a set of 4 data points telling us the exact state of any given electron. Once you know how to read these 4 parts, you can see exactly how the subatomic world is put together. We didn't always know atoms were so complex. In 1913, a physicist named Niels Bohr proposed that electrons orbited the center of an atom in simple, flat rings, very much like planets circling a sun. Because these rings were flat and predictable, scientists thought they only needed a single number, which ring orbital the electron was on, to know exactly where it was. But by the 1920s, physicists like Erwin Schrödinger proved that electrons don't move in flat circles at all. Instead, they exist in active 3-dimensional clouds. Finding an electron in these 3D clouds meant the old flat map didn't work anymore. Scientists had to develop a more detailed 4-part address to navigate this 3-dimensional space. The first part of our quantum address is the distance number, labeled with the letter n. You can think of this as the city. It tells you which main energy level the electron lives in, moving outward from the center as level 1, 2, 3, and so on. The rule here is simple. The higher the number n, the further the electron is from the center, and the more energy it has. Once we have the city, we need the street. Scientists call this the L value, or the shape number. Instead of measuring distance, this number defines the specific geometry of the electron's neighborhood. These shapes start as a simple sphere, grow into a dumbbell, and eventually a complex cloverleaf. They are assigned letters, S for the sphere, P for the dumbbell, and D for the cloverleaf. As L goes up, the shapes become much more intricate. Essentially, N tells you how far out into the quantum city you need to go, while L tells you the geometric shape of the street you've arrived on. Now that we're on the right street, we need the house number. In the lab, this is known as M sub L, or the alignment number. Scientists discovered this because magnetic fields make these shapes point in different directions. A dumbbell shape might be pointing up and down, left and right, or forward and backward in space. The physical shape of the cloud stays exactly the same. The number just tells us which way it's tilted. This alignment number locks in the exact direction the electron's neighborhood is facing, confirming which specific house you are looking for. There's just one final problem. Each of these orbital addresses can hold exactly 2 electrons. So if 2 roommates share the same house, how do we tell them apart? In the 1920s, a physicist named Wolfgang Pauli realized that electrons have a built-in property called spin. This gives us the spin number, or M sub s. An electron has only 2 options. It can have a spin-up state or a spin-down state. This led to a strict cosmic rule. No 2 electrons in an atom can have the exact same 4-part address. If 2 electrons share the same distance, shape, and orientation, they must have opposite spins. They simply cannot exist in the same space if their addresses match. This rule acts like a subatomic bouncer, making it mathematically impossible for 2 electrons to double book the same spot. Looking at this summary, we can see the full address, check the distance, find the shape, identify the direction, and verify the spin. Because electrons aren't allowed to share the same address, they are forced to stack outward, one by one, in very specific mathematical patterns. This orderly stacking is what actually builds the periodic table. Each new row and column in the table represents electrons filling up these shapes and levels in a precise sequence. Because of the way these electrons are organized, atoms are able to link up with each other. This is why different elements can stick together to form the solid matter that makes up everything in the world around us. Even though the world of the atom is too small to see, it follows a system as organized as the mail in your neighborhood. And now you know how to read the address. Thanks for watching.